Hello everyone. In this video, we can see insulation resistance and capacitance of underground cables. In a cable, the main parameters are resistance and capacitance. The insulation resistance of single core cable. A cable conductor is provided with suitable thickness of insulating material in order to prevent leakage current. The conductor will have number of layers and a suitable thickness of insulating material is provided in order to prevent the leakage current. The path for leakage current is radial through the insulation. The opposition offered by the insulation to leakage current is known as insulation resistance of the cable. So, for satisfactory operation, insulation resistance of the cable should be very high. So, we can find the insulation resistance of a single core cable. Consider a single core cable with conductor radius R1 and the total radius R2, including the insulation. Consider a part of the cable at distance x from the center with a thickness dx. Then the insulation, the cross sectional area of the layer will be 2 pi x into length L. If length L is the length of the conductor, then 2 pi x into L will be the cross section of the area of the section. Then insulation resistance is R equal to rho L by A. Rho into here length is dx and A is 2 pi xl. So rho into dx by 2 pi xl. Insulation resistance of total cable is R equal to R1 to R2 integral R1 to R2 rho L by A. That is rho by 2 pi L integral R1 to R2 1 by x dx, where x is the variable. So it is 1 by integral of 1 by x is log x, rho by 2 pi L log R2 by R1. That is the insulation resistance of the cable. This shows that insulation resistance of the cable is inversely proportional to the length. Or if the cable length increases, insulation resistance decreases. Now we can see capacitance of single core cable. In a single core cable, here we can consider the conductor diameter is small d, so the radius is d by 2. Total diameter is capital D and the radius is d by 2. And the insulation is having a relative permittivity of epsilon r. So here also consider a portion with thickness dx. Then the area of the cylinder is 2 pi x into L. L is considered that it is having an axial length of 1 meter. So the area is 2 pi x into 1, that is 2 pi x meter square. Now we have electric flux density. Electric flux density equal to charge by area. If Q is the charge, then Q coulombs is the charge. Q by 2 pi x is the electric flux density dx. Electric flux density equal to electric field intensity into permittivity. Or electric field intensity depends on the permittivity of the material. At a point P, electric field intensity depends on the material at P. So it is equal to dx by epsilon. Epsilon is the permittivity, that is epsilon 0 into epsilon r. So E equal to Q by 2 pi x epsilon 0 into epsilon r volts per meter. Now work done in moving unit positive charge from P through a distance dx in a direction of electric field is Ex dx. Hence, the work done in moving a unit positive charge from conductor to the sheath, which is the potential difference V between conductor and the sheath. Potential difference is the work done in moving a charge from this conductor to the sheath. So, it is integral of d by 2 to d by 2 Ex dx. So, Q by 2 pi x epsilon 0 epsilon r dx We have to integrate from d by 2 to d by 2. So 1 by x is their variable. So log x from d by 2 to d by 2 is log d by d. So the capacitance of the cable, this is the potential difference. So the capacitance is Q by V. So Q by V, while we are substituting the value of V, we will get it as 2 pi epsilon 0 epsilon r log d by d farad per meter. So substitute epsilon value of epsilon 0 as 8.854 into 10 raised to minus 12 into ER by log to the base E. So we can convert it into log to the base 10 as 2.303 log 10 d by d, or epsilon r by 41.4 log to the base 10 d by d into 10 raised to minus 9 farad per meter. So if cable is having a length of L meters, this is the capacitance per meter. So the capacitance will be epsilon r into L by 41.4 log d by d into 10 raised to minus 9 farads. Now we can see dielectric stress in single core cable. Under operating conditions, the insulation of the cable is subjected to electrostatic forces. This force is called dielectric stress on the insulation. Dielectric stress at any point in a cable is actually the potential gradient or electric intensity at that point. So electrical intensity at a point Ex equal to Q by 2 pi epsilon 0 Er into x volt per meter. So electric intensity is equal to potential gradient. Therefore, potential gradient G at point x meters is G equal to Ex. So G equal to Q by 2 pi epsilon 0 Er into x volts per meter. That is the dielectric stress. So we have derived the equation for V as Q by 2 pi epsilon 0 Er log d by d. And then from this we can write Q as 2 pi epsilon 0 Er V by log d by d. Substituting the value of Q from the equation 2 in equation 1, this potential gradient equation, then we will get G equal to 2 pi epsilon 0 Er V by log d by d divided by 2 pi epsilon 0 Er into x, that is V by x log d by d. So it is clear from the equation that potential gradient varies inversely as distance x. Therefore, potential gradient will be maximum when x is minimum. The x is the distance from the center. So x is minimum at d by 2 at the surface of the conductor, or potential gradient will be minimum will be, will be maximum at the surface of the conductor and minimum at the surface of the sheath. The surface of the conductor, potential gradient will be maximum, and at the surface of the sheath, potential gradient will be minimum. So maximum potential gradient can be found out as G max equal to 2V by D log D by D. Here we are putting x equal to small d by 2, and minimum potential gradient we are putting x equal to capital D by 2, then we will get 2V by log D by D. Now we can see problems relating to this. A 33 kV single core cable has a conductor diameter of 1 centimeter and a sheath of inside diameter 4 centimeter. Find the maximum and minimum stress in the insulation. Here we can directly use the equation for G max and G minimum for finding the maximum and minimum stress. G max equal to 2V by D log D by D. Here V is given as 33 kV and small inner diameter is 1 centimeter and sheath diameter is 4 centimeter. Substitute that and we can find the maximum value as 47.61 kV per centimeter. Similarly, G minimum, substitute the values, then we will get it as 11.9 kV per centimeter. Or we can find once if if we found out G max, then we can find the G minimum as G minimum equal to G max into D by D. Then and next question, the maximum and minimum stresses in a dielectric of single core cable are 40 kV per centimeter and 10 kV per centimeter respectively. If the conductor diameter is 2 centimeter, find thickness of insulation and operating voltage. Here G max and G minimum are given. We are asked to find out the capital D thickness of insulation and also voltage V. So here we have a ratio G max by G minimum equal to D by D. So we can have the value of G max, G minimum and cap D. So we can find the value of capital D as G max by G minimum into D, that is 8 centimeter. Substitute the values, then we will get it as 8 centimeter. This is the total radius. So what will be the thickness? Thickness will be D minus D by 2. 8 minus 2 by 2 is 3 centimeter. Now we are asked to find out the operating voltage. To find out the operating voltage, we can substitute in G max or G minimum equation. Any equation can be used. Here G max equal to 2V by log D by D. Substitute that. Then V equal to G max D log D by D by 2. Then we will get the potential operating voltage as 55.45 kV. Thank you.